Hi, today we are going to talk about energy, and energy is one of those things that you have heard and used the word probably for most of your life. There are days when you wake up and say you have a lot of energy or you don't have any energy, and that means different things to different people. But we all know that feeling and we have a sense for what we believe energy is. We're going to use energy in a very specific way in physics. And this introductory video PowerPoint is going to help us all get on the same page so that we all kind of know that we mean the same thing when we talk about energy in class. So, for our purposes, we are going to define energy as the ability to make change. And you have probably heard in middle school or in some of your other high school science classes about conservation of energy, or really the first law of thermodynamics, which states that energy cannot be created and it cannot be destroyed. There's only really two things you can do with energy. You can store energy, or you can kind of move it around between storage modes or storage areas. You can transfer energy. This leads us into what we are going to call the 1, 2, 3s of energy. These are the three things that you need to know and remember about energy, and they're not hard. So the 1, 2, 3s of energy are as follows. Number one, there is one kind of energy, and we call it energy. Energy is energy. You may have heard in middle school or even in some of your other high school classes that there are different forms or types of energy. There really aren't. Energy is energy, okay? And we use a big capital E to symbolize energy. There are two things that we can do with that one kind of energy. We can store that energy in different kinds of places, or we'll call them modes. And we can transfer that energy between storage modes or storage areas. And finally, there are three ways to transfer the energy. There's something called working, that we're going to symbolize with a W, radiating, which we're going to symbolize with an R, and heating, which we're going to symbolize with, for some reason, a Q. Now, we'll talk a lot more about what working and radiating and heating mean. Working really is going to involve forces, and we will talk a lot more about that later and what that means. Radiating is going to involve waves, electromagnetic waves. Those are supposed to be waves, guys. And heating is going to involve the transfer of thermal energy or heat energy by conduction, convection, or sometimes radiation. That gets a little tricky. But we will mostly talk about heating when we talk about friction. Anytime that we are going to consider friction in a problem, we're going to have to think about the heat that results from friction and where that heat goes, how that heat is being transferred into other storage areas in our physical situation. So the 1, 2, 3s of energy, they're super simple. You need to memorize them. Number one, there is one kind of energy. We call it energy. There are two things we can do with that energy: store it and transfer it. And there are three ways that we can transfer it: through working, radiating, and heating. Now let's take a look at where we are storing energy in the common kinds of physical situations that we're going to be dealing with in this class. And we call these energy storage modes or energy storage areas, and some of these words are going to sound very familiar to you, and others of them are going to sound brand new. Most of the time when we think about energy in the terms of a science class, we think about kinetic energy or potential energy, which we'll talk about in just a second. Kinetic energy is really just a storage mode of energy. It's energy that is stored in the motion of an object. If an object is moving relative to us as the one observing it, we would say that that object has kinetic energy. If the object is just sitting there, we say that it has no kinetic energy. So kinetic energy, we symbolize it with a capital E, little subscript K. It's the energy stored in the motion of the object. Gravitational energy, this is something that you have probably heard referred to as potential energy in your life. We're going to try to be very careful about how we talk about energy. We want to try and call energy energy all the time because there is only one kind of energy, and it is called energy. And it has the symbol capital E, and that's why all of those symbols have a capital E. And then we designate the area in which that energy is stored, or we designate that with the little subscript. So gravitational energy is energy stored in the position of an object in a gravitational field. That may be something like the gravitational field of the Earth, and we have a certain gravitational energy based on whether we're standing on top of the Earth on the ground or whether we're jumping out of an airplane with a parachute. And we'll talk about how do we figure out how much gravitational energy an object is storing. Elastic energy is energy stored in the stretch or the compression of an elastic material. This is like a scrunchie. Like if you're going to put a scrunchie in your hair, you grab it, you stretch it out, you wrap it around your hair a few times, and then you let go and you let it snap back into place. Stretching out the rubber band inside the scrunchie, you are stretching an elastic material that just wants to go back to the way it was at the beginning. And in that stretch, we are storing energy in that rubber band inside the scrunchie. You can do the same thing if you compress a spring, for example, and you kind of smush it. It wants to pop back open. We have two kind of symbols for this, either EEL for elastic energy, or I tend to use E little subscript S for like springy energy. And that's because we get into trouble when we start to talk about electric energy, because we often use EEL for that as well. You're welcome to use whatever you want as long as you're real clear about what kind of problem you're in and which energy storage mode you're specifically referring to. Thermal energy, this involves heat. And all heat really is it's caused by the vibrations of atoms. And so something that's very hot has a lot of heat. The atoms are vibrating really fast. And something that's cold, they're vibrating really slow. You can almost think of thermal energy as like the kinetic energy of little tiny atoms. For our purposes, we're going to be dealing with thermal energy mostly in the context of friction. Chemical energy, energy stored in the chemical bonds of substances. We're not going to do a terrible lot with that. We may mention it here and there. That's more of what you would be studying in chemistry class. Internal energy is energy internal to a substance based on its internal structure. Is it a solid? Is it a liquid? Is it a gas? Is it plasma? It really has to do with the state of matter and the arrangement of the atoms and such, molecules. Electromagnetic energy, this is energy stored in electromagnetic waves or light. And finally, kind of the most interesting one, mass. I'm old enough that I grew up, and I think most of us still grow up thinking that mass, matter, energy, stuff, that stuff and energy, matter and energy are different things. That, you can put your hands on stuff, you can't grab energy. And so really, Albert Einstein in the early part of the 20th century came up with that brilliant, eloquent equation, E equals mc squared. The E here is energy, and the M is mass. And it's a little slightly more complicated than that, but and what it basically says is that you can actually kind of turn one into the other. You can sort of freeze energy into mass, into stuff, and you can take mass and you can release energy. And when you do that, there is an enormous amount of energy stored in just a tiny little bit of mass. This c is the speed of light. And remember, that's a huge number, 3 × 10⁸ meters per second, and you're squaring that. And so all you need is a tiny little bit of mass to get a great big amount of energy. And that is kind of the foundation of the atomic bomb and atomic power, nuclear power. We're not going to do a ton with that, but I want you to understand that mass is a storage mode, a storage area for energy. It's not a separate thing that is totally unlike energy. Now, just a short aside about potential energy. It is a word that we have heard most of our lives. I grew up hearing it, kinetic potential, kinetic potential. And usually when I was hearing it as gravitational potential. But there are a couple of sort of different ways of using that word potential energy with different energy storage areas or modes. And basically, when we talk about quote unquote potential energy, we're talking about energy that is stored in an object because of its position in a field or compared to some zero position for that object. It's often used to refer first and foremost to gravitational potential energy. Most of us are familiar with the example of a rock sitting on top of a hill. As long as it's just sitting there and it's high up on the hill, it has gravitational or potential energy. And then as soon as it starts rolling, that is converted or transferred into kinetic energy. It's okay if we want to use the term potential. I would much rather, I want to hear that gravitational though. I want you to start kind of trying to think about, okay, being as specific as possible when you talk about a situation. Elastic potential energy, that's that energy that is stored in like a scrunchie or a spring because it's been stretched out and it wants to snap back to its, what we would call its zero position or its equilibrium position. Or like a spring that would get stretched and then want to snap back, or would get smushed down and would want to pop up. That's all elastic potential energy. And finally, in electricity, we can talk about electric potential energy, which is not quite the same thing as electric potential, which is another term that's used. But this is the energy that's needed to move a charge against an electric field. We're not going to do a lot with that either. If you take Physics 3-4 next year, if we manage to offer it, then that's something when we would do a lot more with electricity at that microscopic level, what's actually happening to charges and to charged particles. So to sum up sort of, potential energy, it's a word, it's not a taboo word. It's just a word that has been used to suggest that there are different kinds of energy, when really there are not. There's one kind of energy. And so I would much rather talk about gravitational energy than talk about potential, because it's kind of a sloppy way of talking about it. And I'm going to push you and myself to constantly be as specific as possible. Now, whenever we approach an energy problem or we look at a situation and we want to analyze what's going on with energy in this situation, we're always going to begin by defining the system. The system is whatever part of the physical universe around us that we are going to look at and analyze. It includes all the objects that we are going to pay attention to, and it might also include things like the air that objects are moving through. Sometimes it's much easier to include that air in the system, and we'll see why as time goes on here. Everything inside the system is the system. Everything outside the system is either known as the surroundings or the environment. And we generally ignore what is happening in the surroundings, in the environment, unless it has some effect on the system, unless something happening out there is going to come into our system and affect it. The great news about systems is that usually we as physicists can define the system. because we want to look at only a few things, a few specific objects, or one specific situation, and we can define the system in the way that makes it the easiest for us to analyze that situation. And so I'm going to teach you how to define the system, and we're going to work on always defining the system that we're looking at as we go forward. There are two kinds of systems for our purposes. First of all, we're going to have a closed system or an isolated system. There are some people who would divide those and have certain small differences between them, but we are going to consider them synonyms, basically the same thing. No matter, no stuff, and no energy leaves a closed or an isolated system. Okay, and no matter or energy comes into the system. All of the stuff and all of the energy that we are going to look at and consider is in that system when we begin, and it's still in that system when we are done, and there has been nothing added or taken away. That's a closed or an isolated system. Closed or isolated systems are very handy. They are very, very helpful to calculations if you can find a way to define your system as a closed system. Open systems are a little bit different in that matter or energy does either leave the system or come into the system from the surroundings. And so the most common time that we're going to deal with open systems is if we have thermal energy, heat being created usually by friction, and then that heat energy is being transferred out into the environment or into the surroundings. And we'll talk about that more as we go. The powerful thing about having a closed or an isolated system is that the total amount of energy in that system is always the same. Because no energy is coming in, because no energy is going out, you always have the total amount of energy. And that means that you can start to solve problems in a pretty straightforward way that might otherwise be pretty complicated. And we'll see what we mean by that. And if you hear someone snoring, that's my dog. My dog is sitting here right beside me snoring while I'm doing this. So say hello to Jasper, everybody. Jasper, you can stop snoring anytime you want. We would consider the universe itself as sort of the ultimate closed system because no energy leaves, nothing comes in from outside because we don't believe there is anything outside of the universe. And within the system, energy can be moving around all the time. Energy can be transferred between storage modes in all kinds of ways. And so we will pay very close attention to that. The power, though, is in the fact that the total energy before is always equal to the total energy after. Remember this little sigma symbol? That's a sigma. And it means the sum of all the energies before in a system is going to equal the sum of all the energy after, whatever happens in our system. This is conservation of energy. No energy is gained, no energy is lost, none is created, none is destroyed. We have the same overriding amount of energy total in the system all the time. It is an incredibly powerful law in physics. There are a few of these conservation laws that we are going to come in to contact with over the course of this semester together, which is a year together. And conservation of energy is our first one. Okay, so let's consider how we work with this idea. Now, let's say a ball is held about 1.5 meters above the floor. Here we go, guys. I'm going to start my fantastic drawings. All right, so say I have a person standing here holding a ball, and that is 1.5 meters above the floor. It is then dropped, whoosh, to the floor. And we're going to pretend that there's no air resistance, there's no friction with the air, anything, okay? What I would say here is that my system would include the ball and the floor. I don't have to think about air because I'm ignoring the effects of air in this situation. And that means that there's no energy coming in from anywhere. I'm not going to be losing any energy with heat and friction going off into the air, into the environment. And so I have a closed system. In a closed system, energy is conserved. And that means that the total amount of energy before I drop the ball is the same as the total amount of energy after I've dropped the ball at every point. Now, what I can do is I can write a conservation of energy equation. And this simply lists all of the storage modes for energy that I have before. In this case, when I'm holding the ball up here, the ball is not moving, so I don't have any kinetic. There's no elastic energy. There's no thermal energy. And we're not going to generally care about internal energy and those types of things. And so all of my energy here is going to be gravitational, E.g. For my purposes, I'm going to say that the floor right here is gravitational 0. That's where E.g. would equal 0. And we'll talk a lot more about that together. And so when I drop the ball, what does the ball start doing? It starts falling. It starts moving. And that means two things. Number one, it starts to pick up kinetic energy because now it's moving. So kinetic energy starts to go up. And because it's going down, it's getting closer and closer to the gravitational 0 line, which means that the gravitational energy is decreasing until right here, right before I hit the ground, just before it hits. I pretend that I'm essentially hitting the ground, but it's just before. At that point, there will be no gravitational energy, and the ball will be moving the fastest, so it will be all kinetic energy. And the gravitational energy before I drop the ball will equal the amount of kinetic energy after I drop the ball just before it hits the ground. That's a conservation of energy idea. There's no energy that comes in, there's no energy that leaves. So what you start with in terms of how much energy you're storing, it has to be equal to what you end up with. But it might be stored in a different storage mode. In this case, kinetic in the motion of the object rather than gravitational in the position of that ball in Earth's gravitational field. Let's look at the second one. So in this case, here's my floor again, and that's my gravitational 0 at the floor there. And now the ball is just kind of falling through the air. That's my way of showing that the ball is falling through the air. This is excellent. Okay. And again, I'm ignoring air resistance. I'm ignoring friction. And the ball is headed downwards like such. Again, the system is going to include the ball and the floor. Because I don't need to worry about the air. I've been told I can ignore that. And the only things, objects involved here are that ball and that floor. And so I do have a closed system. I don't have energy coming in. I don't have energy leaving in the form of heat from friction. And so I have a closed system where energy is conserved. That means that the total amount of energy that I have before, at the moment that I'm considering the ball, has to equal the total amount of energy after. And so what I do is I go in here. Here's my first kind of snapshot, is right here, okay, where this ball has already fallen some, but has not fallen the whole way to the ground. And if I think about where is my energy being stored, well, first of all, the ball is falling, it's moving, so I have some kinetic energy, and I'm still a distance above that gravitational zero line, so I've got to have some gravitational energy too. So that's before. After the ball has fallen more, just right here before it hits, I'm no longer going to have gravitational energy. I'm going to have all kinetic energy. And so the equation that I would write from my kind of before snapshot, which is really halfway through the ball's motion, I'm going to write gravitational energy plus kinetic energy here is equal to the kinetic energy total at the end. And that's my conservation of energy equation. Now, right now, we don't know how to calculate gravitational energy. We don't know how to calculate kinetic energy. The formulas are very straightforward, and we're going to learn them soon. And when you know that, you can suddenly solve for a whole bunch of different variables. And it becomes incredibly powerful, and yet it's very straightforward how you set the problem up. Then the issue just becomes doing the math. All right, and finally, our last example is our most complicated example. Again, I'm going to kind of draw my floor, which is more of a mess than usual. This is my gravitational zero line. And again, I have my ball that's kind of falling through the air straight down. It's already kind of flying down. I say that my system includes the ball and the floor. But in this case, I'm doing something different than I did before. I'm considering air resistance. Air resistance is simply friction with the molecules of the air. Friction is, for our purposes right now, it's kind of like when you rub two objects together. If you take your hands right now and rub them together real fast and real hard, what do you notice happens to your hands? Take just a moment and do that. What happens to your hands? They get really hot, don't they? And you can kind of put your hands on your cheeks and you can feel how warm your hands got. That's because of friction. Anytime you have friction, you generate heat. You transfer energy into heat energy, thermal energy, and then that is transferred by Q, by heating. Generally, we consider that transferred out of the system into the air. And so we have that happening, except instead of like your two hands rubbing together, we have the ball kind of rubbing up against molecules in the air and air resistance. Now, that means for our purposes that the system is going to be open. We are going to be transferring heat out into the surroundings or the environment. So even though energy is not conserved, we can still write what could be a helpful equation for us. And here's how we would do it. Our situation with the ball at this kind of before snapshot is the same as it was in the last slide. We have right here some gravitational energy, and we have kinetic energy because the ball is moving and it's falling. We also, as the ball moves and falls, we are transferring this thermal energy, this heat out of the system, and what we use for that mechanism is Q. It's heating, and I will often write Q out, meaning the heating is transferring the energy out of the system into the surroundings. And then by the time we get right up to the edge of the floor there, we've lost our gravitational energy. That has been transferred into the motion of the ball, the kinetic energy, which is now going really fast. And we have all kinetic energy, except there's not a complete amount. We've lost some energy. So if we go to write our equation, our gravitational plus our kinetic energy here halfway through as the ball falls, it's not equal to just the kinetic energy at the floor. You have to figure in how much energy has been transferred out of the system by that heating. And so I would add the amount of heating energy that was transferred out. And that's all there is to this. We call these equations here conservation of energy equations. And right now, all you have to do is this. I need you to recognize what storage modes we're working with, what transfer of energy mechanisms we're dealing with, and then we're going to learn to put all of this together into a certain type of diagram and these conservation of energy equations. That, my friends, is it for now.